In physics, we will often need to work with vectors. So let's see how we work with vectors. In this particular case, let's take a look at how we add two vectors. Let's say these are displacement vectors, the red vector and the green vector. And using the tip-to-tail method, we can see that those two displacements add up to the green vector using the tip-to-tail method. But what if you can't find the length of the green vector that easily? So we're going to take a look at another way of doing it, and that is, when working with vectors, it is always going to be convenient to resolve a vector into components. What this means is to take a vector like v here on the right and replace it with components, vx and vy. You can take the vector away. If we know the length of this vector, v, and we know this angle here, theta, we can always calculate the components by using some simple trigonometric equations. For example, the sine of this angle theta is equal to opposite over hypotenuse, so it's vy over v. And solving this for vy, we get vy equals v sine of theta. Similarly, the cosine of the angle theta on that triangle is adjacent over hypotenuse. Solving that for vx, we get vx equals v sine theta. Also, if we know vx, vy, we can find the angle using the tangent, which is opposite over adjacent, or vy divided by vx. And so what this means is that if we have a vector, v, we can actually replace that vector with its components. It turns out that very often it is easier to work with the components than to work with the original vector. As an example, let's say we want to add these two vectors, a and b. Well, if we use the tip-to-tail method, we put this one here, and the green vector, therefore, is the resultant of those two. But let's do it another way. What we're going to do is we're going to resolve each vector into components. Now, in this case, we can just read what the components are. So, for example, the x component of the vector a is just this distance here. And the y component is this distance here. We can read those because we have this graph. And the components of a are these numbers. The x component here is -7, and you can count that off, see it, 1, 2, 3, 4, 5, 6, 7. It's negative. And the y component is 1, 2, 3, 4, 5. We can do the same thing with b. The x component of b is +37, and that means this distance from here to here. And the y component is 7. That's the distance from here to here. So what that means is that we can remove a and b and just leave the component vectors. And those are easy to add. So the x component of the resultant is going to be this minus that. And the y component of the resultant will be this plus that. And if we do that, we find the resultant, the components of the resultant, which is the sum of those two vectors, to be -4 and -12. So basically, we're adding these two numbers to get the x component and these two numbers to get the y component. And you can see this is the components of the resultant. If we put the resultant in here, we can see that this vector has these components, -4 -4 is the x component, and +12 is the y component of the result. So here's the resultant. How do we calculate, in fact, the length of the resultant and what this angle here is? What is this angle? Well, we're going to resolve that we're going to look at that vector r in terms of its component. This is the x component, and this is the y component. We know what those are. We know that they are minus 4 and 12. So this is 4, and this is 12. So how do we find what r is? Well, again, using the Pythagorean theorem, 12 squared plus 4 squared will give you r squared. And that's 160, so r is 12.65. 12.65. And what's this angle theta here? Well, theta is going to be the leg opposite divided by the leg adjacent. The tangent of theta will be the leg opposite divided by the leg adjacent, which is 12 divided by 4. Which is 3. So I made a mistake here. 12 divided by this equals 12 divided by 4, which is 3. And the inverse tangent or arctangent of theta will be the arctangent of 3. Now the arctangent of 3 is not 37 degrees like I had here, but it is 72 degrees. So this angle theta right here is 72 degrees. So see if you can do this problem. Stop the tape and see if you can find the components of each of these two vectors here, and then the components of the sum C, which is the sum of those two vectors. And then sketch C in the graph above and calculate its magnitude. Now we can see that using the tip to tail method what this is going to look like, that this green vector here is going to be the vector C. Now it's going to have negative components. You can see the x component is negative. I'm sorry, the y component will be negative, but the x component will be positive. Let's see if we can calculate those. So the x component of A is this distance here. 1, 2, 3, 4, 5, 6. And it's going to be minus 6. The y component will be 1, 2, 3, 4, 5, minus 5. It's this distance. The x component of B is going to be 10. And the y component of B is going to be 3. So the x component of their sum is going to be 10 plus or minus 6, which is 4. And 3 plus or minus 5, which is minus 2. And so you can see this is minus 2, minus 3, I'm sorry. Minus 2, minus 3, depending on how well you read it. I happen to have read it as 4 minus 3 instead of 4 minus 2. In any case, the resultant, the length of the vector C is going to be 5. And so this is C, what it looks like. It has a y component of 1, 2, 1, 2, 3, 4. An x component of 4 and a y component of minus 3. So here's another problem for you to try by yourself. Stop the tape, and I'll just put down the answers here. The x component of A is this distance, and the y component of A is that distance. So A is minus, that's the length of the red line, minus 6.4 approximately, and that's his x component, and his y component is the blue line here, that's 7.8. Same thing with B. You add the two numbers, and you get the coordinates of the result. A real problem is this example of Huck Finn walking across his raft. He walks across the raft at 1 meter per second, but the raft is traveling down the river 2 meters per second. What is the magnitude of Huck's velocity relative to the river bank? Well, this is what's happening. Basically, what we're doing is we're adding these two vectors. 1 meter per second is his walk this way, and 2 meters per second the river is going. His resultant velocity will be to the right.